We're very happy to have Philip Engel, Matroids, and the integral Hodge Conjecture for Abelian Varieties.
Thanks. Thank you for the invitation. This is all joint work with Olivier, Fortman, and Stefan Schreider. So let me start just by talking about regular matroids and their relation to principally polarized abelian varieties. So we don't need a general definition of a matroid, just a regular matroid, so I'll give something specialized to that situation. So for us, a regular matroid let's call it R, is a finite set of vectors, let's say xi, indexed by some set 1 through k. So this is a subset of z to the g, satisfying the following two conditions. So first is that the xi generate z to the g. And the second is that any subset of the xi generate a saturated subgroup. Okay, so by saturated subgroup, we mean if we quotient by this subgroup, then the quotient is torsion-free. Okay, so what are some examples? For instance, 1, 0, 0, 1, 1, 1, contained in z squared, is a regular matroid on 3 elements in z squared. This g we call the rank of the matroid. So each of these vectors is primitive. So they generate saturated subgroups. And then any pair form a lattice basis. So that's also fine. Okay, so let's do maybe a non-example. If we throw into this the vector 1 minus 1, then we run into trouble. So most of the pairs are fine, but these two, they generate an index 2 sublattice of z squared, which is then not saturated. Okay, so now I'll give a general class of examples that you can associate to a graph. So let's let G be an oriented graph. We'll define the cographic matroid of G to be the set of edge duals. So these are elements of the first cohomology of G with coefficients in Z, and the indexing set is the set of edges of the graph. Okay, so these are the linear functions on the homology. Now I can see in a loop in the graph, I can see how many times does that loop go through the oriented edge EI. And so that's a linear functional on the homology, so it's an element of the cohomology. So this is what we call the cographic matroid. And let's do an example. So if we take this theta graph and we orient the edges like so, E1, E2, E3, so then the first homology of this graph is generated by, well, this loop, E1 plus E3 and E2 plus E3. And so if we look at the set E1 dual, E2 dual, E3 dual, so E1 dual is 1, 0 because it extracts the E1 coefficient, right? E2 dual is 0, 1, and E3 dual is 1, 1. So we see that, in fact, our first example is an example of a cographic matroid. Okay, and then the sort of last general class we'll consider is the graphic matroid. And what we do is we take the edges in the free abelian group generated by the edges, but then we reduce mod the homology of the graph. Okay, so as we said, the first homology embeds naturally into the free abelian group on the edges because we have an orientation. We take the image of the standard basis in the quotient. So yeah, let me give this a name. This is the graphic. Okay.
E2 minus E3 and E2 minus E3. I know we've been adding this one.
This one?
Yeah.
Well, the orientation of the edge E3, it goes down. So the loop, yeah.
Only matroids that come from graphs in this way?
Huh?
Are you only going to use matroids that come from graphs?
No, I will also use the R10 matroid. But we'll get to it in a, yeah. So these are regular. Yeah, so these are all regular matroids, well, except the non-example. Yeah. So let's relate these to abelian varieties. Okay, so we're going to build a degeneration of principally polarized abelian varieties out of a regular matroid. Okay, so how are we going to do it? Well, let me first say, okay, so let me call it X star of the matroid R, and it's over a punctured polydisk. Okay, so this is a family. This is going to be a family of principally polarized abelian G-folds, where G is the rank of the matroid, and this K is the number of elements of the matroid. Okay, so that's for the G and K, how they relate to the matroid. Okay, so how do we build it? Well, we'll build it using its period map. So we'll take the universal cover of this. So this is the upper half plane to the K. Let's call this X tilde star of R. And now all we need to do is specify a period map from the kth power of the upper half plane to the Siegel space, right? Because then we can just pull back the universal family over Siegel space and get our family. Okay, so this should be appropriately equivariant for the monodromy. Okay, so what is this map? Well, we just send a point, let's say tau 1 through tau k, in these k copies of the upper half plane to the following matrix. So it's tau 1, x1, x1 transpose, plus tau 2, x2, x2 transpose, plus tau k, xk, xk transpose. So I claim that this is interpreted as an element of the Siegel space. How do I interpret it? Well, the point is that I took this vector, right? So, okay, by convention, maybe it's a G by 1 vector. So when I multiply it by its transpose, I get a G by G matrix, a rank 1 G by G matrix. This is an element of sim G by G of Z. And it's a positive semi-definite matrix with a null space of rank G minus 1. Okay, so because the xi generates Z to the G, this is not just positive semi-definite, but actually positive definite. Okay, so that's our map. And now we should descend it down to the punctured polydisk. So we need to describe the monodromy. Well, let me just maybe put it over here. What is the monodromy of this family? Well, we can conjugate it into the sort of standard unipotent in the symplectic group. So we can have some identity blocks here, and then here, well, when tau I goes to tau I plus 1, we add this matrix, right? So so this is the monodromy about the ith coordinate hyperplane of the punctured polydisk.
So in this definition, you use the obvious billionaire form on the Z, but there is not such a basis in the case of the matroid MJ.
Yeah, so here we're kind of identifying this, the xi's, let's say, okay, in the case of, let's say, a cographic matroid, the xi's are elements of the H upper 1 GZ. So these are naturally Well, okay, so they're naturally, I guess, in sim 2 of this, so they're quadratic forms on H lower 1 of the graph. So the H lower 1 GZ here is the how I'm taking yeah. So or I mean, you can really just concretely think of them as vectors, and then we're like literally just taking this period matrix. So yeah, this will be the monodromy about the vanishing of ui, where this is a coordinate hyperplane in the polydisk. So it's where the ith coordinate vanishes. Let's see in our example, in fact, what this looks like. So
I was expecting to see that was cool. I was expecting to see some polyhedral decomposition.
we will, yeah, when we extend this family to over the polydisk, there'll be a Mumford construction. Yeah, so in example 1, we get tau 1 times 1, 0, 0, 0 plus tau 2 times 0, 0, 0, 1 plus tau 3 times 1, 1, 1, 1. So that is an element of the Siegel space H2. So yeah, we see that these rank 1 matrices are exactly these xi transpose for these 3 vectors. Okay, so that's sort of our that's what's happening kind of on the inside of in the punctured polydisk. And now, yeah, let me discuss what happens. How do we extend this family over the polydisk?
So how come that matroid thing matters here? I see what you want for rank, but how about the definition? Where is it?
Yeah, so right now it doesn't matter. Like we could have done this with any set of vectors, right, that generate like even over Q. Yeah, but so we'll see that the regularity of the matroid implies the regularity of the degeneration. It'll be a smooth total space. So theorem, there exists a filling of this punctured family. Let's now give a name to the filling. Let's call it XR over the k-dimensional polydisk. Well, of our punctured family, star R over delta star to the k, such that F is nodal. Okay, so I need to define for you what is a nodal morphism of analytic spaces. So definition, f x to y, let's say morphism of analytic spaces is nodal if it is analytically locally of some specified shape. Okay, so what is this specified shape? Well, I take a product of node smoothings. So say J plus L or something. Okay, so let's see what this is. Okay, we start with xi y equals ui, just project it down to the ui coordinate. So if we take a product of those, this is just a product. This is a product of node smoothings. And then this is just projection. So this is a smooth morphism. So a nodal morphism, by definition, is a morphism which analytically locally is a product of node smoothings with a smooth morphism. Okay, and we'll see in pictures what this looks like for our filling soon. But maybe I should remark already that by this local form, we see that the total space is smooth.
And you want F to be proper also, I guess.
F to be what?
Proper.
No, I mean you can define a nodal. Yeah. Yeah. Sorry. Let me say that this filling. Let me say a flat, proper filling. But I mean the notion of a nodal is just a purely local notion about the singularities of a morphism. Okay. So. So I think we'll get a better sense of what is the meaning of a nodal morphism by sort of drawing a picture and then going through the proof of this theorem. So I'll just give a sketch. So the key sort of input is this so-called Mumford construction of degenerating abelian varieties. So yeah, so the setup is as before. R is a regular matroid on k elements in z to the g. So so let's set M to be the dual lattice of z to the g, and then we'll take a torus Tg to be this dual lattice tensored with R mod the dual lattice. Okay, so we can think we have a torus, which maybe we can think of as a square with opposite sides glued, if g equals 2. And inside of this torus, we'll define a hypertorus arrangement by the following condition. Okay, so since M is the dual of z to the g, where our elements xi of our matroid live, xi are linear functionals, right, on M. Okay, so if I take where this linear functional is in a certain coset of z. So this delta I is a random element of Q mod z, randomly chosen. We'll see what random means in a second. Let's see an example of this hypertorus arrangement in the case of our favorite matroid, our theta matroid. So for instance, we have R is these three elements, and then these delta i's, we should think of them as shifts for the three elements. So we'll take 0, 0, and 1/2 as our quote random elements of Q mod z. And now let me draw the locus. So inside our two-dimensional torus, we'll draw the locus where x1 is in z, right? Because the first shift is 0. Okay, that's the two opposite sides of the torus, which are identified. Here we'll draw this locus where x2 is in z. Okay, and then our third locus will be where x3 is in 1/2 plus z. So x3, which recall, x3 is x1 plus x2. So that's x1 plus x2 is in 1/2 plus z. And now we should make sure to glue this up so that we get a torus, a two-dimensional torus. Okay, so that's our sort of hypertorus arrangement inside this torus. Okay, and now you just need to properly interpret this picture, and it will be the central fiber of the degeneration of the filling. Okay, so
You have to choose some delta I later.
we have to choose them, and the condition is that the hyperplane arrangement should be transverse. So there should be no unexpected intersections. In other words, if hyperplanes intersect, if and only if the xi's are linearly independent, is the condition of transversality.
You don't need to decompose into simplexes.
No, yeah, no, we don't need to decompose further. Yeah, we'll just take this decomposition, and this will equal the central fiber of our degeneration. So how do we sort of interpret this picture? How do we interpret this picture as a singular variety? Well, we view it as a polytope. So if you're familiar with toric geometry, you can take a lattice polytope or a Q polytope and output a polarized or Q polarized toric variety. In this case, the three polytopes give you P2, P2, and the blow up at 3 points of P2. And then we take these varieties and we glue them according to the combinatorics of this picture. So for instance, on this P2, there are 3 lines, right? So those are 3 lines on a P2. And then say this line on this P2, which is this blue segment here, it will get glued to a P1 on this surface, on this del Pezzo surface of degree 6. Okay, so in this way, we glue up so that the intersection complex is this tiling of the torus. And now let me say why is this nodal? Well, let's say I look along this yellow segment. This represents a double locus in the surface, right? Where 2 surfaces are glued, 2 smooth surfaces are glued here. So that's locally given by the singularity x3, y3 equals 0. But then as we deform over non-zero U3, we're going to smooth that node. So the local equation along this double locus will be like x3, y3 equals U3. The local equation of the total space along the blue will be x2, y2 equals U2. Sorry for the use of x in multiple ways. One has a vector on it though, so. And this will be x1, y1 equals u1. And then at an intersection, say where 2 of these points meet, then we get the product form that we put over there. And the reason why we don't want all 3 of the colors to intersect at a single point is because we certainly don't get the product because, well, that would be a 6-fold, but in the end, this degeneration is going to be a 5-fold. It's a family of surfaces over a 3, so it would be more like a fiber product than a product. Okay?
So, and what info that fxy equals u and not u squared?
Yeah, so the correct way to do this, I've sort of described the geometry of the central fiber and its smoothing, but the way that you actually construct it is that you take a certain infinite type toric variety that fibers over the 3-dimensional polydisk, and then you quotient that toric variety by an action of z squared. And on the general fiber, it'll be c squared mod, actually, it'll be exactly like this on the general fiber, okay? And then on the special fiber, an infinite periodic quilt of toric varieties will get quotiented to this sort of finite thing. So that's how you actually construct it. And so, for instance, if you want to analyze the local singularities of the morphism, you might as well do it on the universal cover. Yeah.
So delta just be general enough not to have.
Just exactly, just general enough that the intersections are transverse. Yeah, that's right. Okay, so that's it for the construction of the degeneration. Okay, I didn't tell you exactly how it works, but okay, at least you sort of see what the geometry looks like of this degenerating family. Okay, so yeah, so the key point here is that over as you deform U1, U2, or U3 away from 0, either the red, the yellow, or the blue double loci smooth. Okay. Okay, so let me state now the main results. Oh, and maybe I'll just, in words, give a name to this. We'll call this a matroidal degeneration associated to the matroid R. Okay, so the main theorem is that there exists a combinatorial invariant let me call it D of R. So it's a purely combinatorially defined thing in terms of a regular matroid. It's valued in the natural numbers n, such that the following properties hold. Yeah, okay, maybe I'll go over here. Okay, the first is that if xt is a very general fiber, of the matroidal degeneration associated to the matroid R, and CT is a curve on the very general fiber, is a curve, such that the cohomology class of this curve is a multiple of the so-called minimal class. Okay, so maybe I should just say theta here is the class of the, this is the class of the principal polarization, okay? So this is an integer cohomology class, this theta to the g minus 1 over g minus 1 factorial. In the case of a Jacobian, it's famously represented by the Abel-Jacobi image, okay? So if we have a curve on the very general fiber, which represents a multiple of the minimal class, so then D of R divides this multiple. Okay, so that's the first sort of thing. And then the second is a sort of description, to some degree at least, of this multiple. So 2, D of R equals 1 if and only if R is cographic. Okay, so let's deduce some nice corollaries out of this. So corollary 1 is that the integral Hodge conjecture is false for X an abelian variety very general, so long as G is at least 4. This is the best you can do because for abelian, principally polarized abelian varieties of dimension 1, 2, and 3, they're all Jacobians. So of course, the minimal class is represented by an algebraic cycle, which is the Abel-Jacobi image. Okay, so, okay, proof. So the proof is that we'll take R to be the graphic matroid of the complete graph K5. So that's this sort of, pentagram graph.
Is D of R supposed to be the GCD of all the n? Is it like those?
No, I mean, yeah, yeah, it's a lower bound, but we don't know that it's an upper bound. It's not, yeah, we don't, this D of R is sort of, well, it's not optimal. Well, it's optimal up to G equals 6, but it will start to fail to be optimal past G equals 6. Okay, so yeah, like let's take this graphic matroid on K5. So then this degeneration we associated to a regular matroid. So this is a degeneration of principally polarized abelian fourfolds over a 10-dimensional base. Okay, and now I haven't defined it for you, but this D of MK5 ends up being 2. So one way to see that it's not 1 from the theorem is that, well, okay, MK5 is a graphic matroid. A graphic matroid is co-graphic if and only if the graph is planar. Okay, so K5 is famously an excluded minor for planarity of graphs, right? So that tells you that D already can't be 1, so it must be bigger than 1. And so that implies that no odd multiple of the minimal class. So this is not algebraic. So it's not represented by an algebraic cycle on a very general fiber. Because every multiple of the minimal class that's algebraic has to be an even multiple. It's divisible by 2. Okay, so that proves it for abelian fourfolds. And for higher dimensional abelian varieties, you can just degenerate to an abelian fourfold producted with a bunch of elliptic curves.
So for this part, you didn't need a matroid that wasn't coming from a graph.
Yeah, you just need a matroid. You just need a non-cographic matroid. That's all you need. Indeed, yeah. Okay. So corollary 2. So a very general cubic threefold. Let's say Y is stably irrational. Okay, so let's just define what is stable irrationality. It says that Y crossed with projective space is not birational to projective space of dimension, well, in this case, 3 more, because we have a cubic threefold for any n. Okay, so let's see how.
Sorry, Phil, can I ask?
You guys should pause. Yeah, are there questions? Yeah.
So I'm slightly confused. So it seems to me like you for this choice of K5 have built some family whose very general fiber like has the integral Hodge conjecture false, but you're stating there that for any x and AG very general. So is it obvious that somehow you can like for any?
Oh, it's not any x for I would say for an x in AG very.
Oh, okay.
Yeah. Sorry. Yeah. Yeah, that's definitely false. I mean, they're Jacobians in any genus. Yeah, absolutely. So, yeah. Are there other questions? Okay, so let's sort of see how to get the second corollary. So we start with the so-called Segre cubic threefold. So it's defined by the following equations. We take sum of x0 through x5 and x0 cubed through x5 cubed equals 0. Okay, so this is sitting, I guess, inside of P5. But then the first equation, is a hyperplane, right? So I get it into a P4, and then inside that P4, I take a cubic. Okay, so
What are you trying to do?
sorry, I'm proving the corollary 2. A very general cubic threefold is stably irrational. Okay, so this is the so-called Segre cubic. And it has 10 nodes. It's the unique cubic threefold with 10 nodes. Okay? Okay, and now we take the universal deformation of this Segre cubic threefold. So let's call it Y. So this is the universal deformation. So the thing to keep in mind here is that the moduli space of cubic threefolds is 10-dimensional. So we kind of deform this singular cubic threefold with 10 nodes into the 10-dimensional moduli space of cubic threefolds, smooth cubic threefolds. And over each coordinate hyperplane, we smooth one of the 10 nodes. Okay? So what that tells you is that then this y star over delta star to the 10 is smooth because there's a smooth family of cubic threefolds because I smoothed all 10 nodes. And now, famously, the cubic threefold has a Hodge structure on its integer cohomology. So it has a Hodge structure of type 0, 5, 5, 0. So there's an intermediate Jacobian associated to the cubic threefold, which is a principally polarized abelian fivefold. So what we do is we take the relative intermediate Jacobian fibration of this over delta star to the 10. So this is now a fibration. This is a fibration in principally polarized abelian fivefolds. And in fact, it's X star of R10. This is a famous matroid called the Seymour-Bixby matroid. It's a matroid, a regular matroid on 10 elements in Z to the 5. And importantly, it's not cographic, okay? So yeah, this identification that this matroid is relevant to degenerations of intermediate Jacobians, this is due to Gaay in 2000. I haven't looked at the time. 3:06. When did I start? 2:30? Okay. Okay, good. Okay, so we have a degenerating family of principally polarized abelian fivefolds, which is our sort of our kind of punctured family associated to this R10 matroid. And so by theorem 1, we have a filling, right? With theorem 1, we can fill this to an x of R10 over delta to the 10. So this is a nodal degeneration of principally polarized abelian fivefolds. And now we apply theorem 2. So this d of R10 is equal to 2. And so that implies that theta to the 4 over 4 factorial is not algebraic on xt, a very general fiber of this degeneration. But by a theorem due to Voisin in 2017, that implies that the original cubic threefold yt has no so-called decomposition of the diagonal. So this is some cycle theoretic criterion. So she proved the equivalence of 3 statements that this class is algebraic, that yt has a decomposition of the diagonal, and that there exists a universal codimension 2 cycle. So those 3 conditions are equivalent. It doesn't particularly matter, but in the, well, yeah, okay. The point is that it is a consequence of having no decomposition of the diagonal that yt is stably irrational. So maybe this is worth comparing to the Clemens-Griffiths method, which proved the irrationality of cubic threefolds. So the irrationality of cubic threefolds is due to the fact that the intermediate Jacobian is not a Jacobian. Not being a Jacobian, by Matsusaka's criterion, is the same as saying that the minimal class is an effective algebraic cycle. So the stronger condition that not only is it not effective algebraic, but not even algebraic at all. Algebraic, you have positive and negative linear combinations of curves. So that stronger hypothesis implies then the stronger conclusion that it's stably irrational rather than rational. Okay, so
I'm a little confused how you can prove it is exactly and then end up something looking like it or correctly at first order.
it's not exactly x of R10.
But it looks like it does actually.
The monodromy is the same, and this proof ultimately it's topological. So you can deform, there's a topologically trivial deformation of this family to the one that we defined, which is in some sense the nilpotent orbit that slices through the corresponding toroidal boundary stratum. Okay, so
What's the source of D being one if you co-graph?
yeah, well, okay, we'll discuss that next, which is the proof of the main theorem. But yeah, I mean, okay, the point is that this kind of comes from monodromy. We wrote down the monodromy of our family X star of R earlier. And the point is that if you have a degeneration of Jacobians,
You wrote down the generator.
yeah, I wrote down what each loop in pi1, maps pi1 of the punctured polydisk maps to, right? Is this identity xi transpose 0 identity. So the point is that when you have a degeneration of Jacobians, the monodromy is governed by the cographic matroid. And the cographic matroid of what? Of the dual graph of the nodal curve. So the curve degenerates to a nodal curve, and then out of that nodal curve, you extract a graph, which is the dual graph. And the Picard-Lefschetz formula describes the monodromy of that degeneration of curves in terms of the dual graph. And the point is that these matroids are kind of fundamentally fundamentally don't fit inside graphs somehow. So we'll see, give a more precise description.
Sorry, can you say why you know it's not algebraic on XT?
It's because by this property, every algebraic curve on XT represents an even multiple.
Oh, I see.
Even so any odd multiple again is not algebraic. Okay, maybe I'll keep this statement at least if you want to. So okay, proof sketch. The theorem, we need to impose, to avoid a lot of technicalities, we're going to impose a simplifying hypothesis. And in fact, that will bring me back to something that I should have already commented on, which is that we're going to assume that CT is a curve on the generic fiber. Okay, so what's the difference between a very general fiber and a generic fiber? Well, a very general fiber is just some fiber away from a countable union of subvarieties, okay? On the generic fiber means that the curve actually spreads out over a Zariski open set of the polydisk, or some algebraic approximation of the polydisk. So in the end, you should actually do everything algebraically and work over a smooth quasi-projective base, which has a polydisk chart. But okay, let's ignore the subtleties. So what is the, okay, so yeah, now, okay, so we'll assume that it's a curve on the generic fiber such that the curve represents m times the minimal curve class. And now, well, yeah, as we said, this implies that it sort of spreads out to give a curve, let's say C sub u over u. So here we have our matroidal degeneration, and this u is now a Zariski open subset.
Very cool. Do you practice on finite cover of this polydisk to arrange for the simplifying hypothesis?
That's no, I mean the correct way to get rid of the simplifying hypothesis is to pass to, what you have to do is you have to first pass to a generically finite cover of this, and then you have to pass to a semi-stable resolution of the inverse image of the coordinate hyperplanes. And then you have to do some complicated combinatorial descent. So we're going to avoid all those steps by assuming that the family of curves actually lives on the original base. And that's the simplifying hypothesis.
But that combinatorial procedure might have changed R for it.
It doesn't change our like it's because the monodromy, it's like the image of monodromy or whatever, which is going to be the same sort of whether you base change or not, you know, up to finite index. Okay, so okay, so what's the point? Let me give a name to this map. I'll call it iota. So now the key is that x of R is smooth. Smooth, and also F is flat. So because the total space is smooth, we have access to essentially like moving lemmas. So by a sort of Bertini style / moving lemma, this is sort of critically where we use the smoothness. There's some, we get to replace C. Oh yeah, wait, maybe I should say what is C. Sorry. C here is the Zariski closure of the curve over the generic, over the Zariski open. Okay, so the issue with this curve, this closure of the curve over the open is like, this could be horrible. Like this may not be equidimensional over the base. For instance, like we're over a large dimensional base. The closure of this family of curves could even contain the entire central fiber. You know, that would be possible. So we want to replace it. So we'll replace C with a curve which is transverse to the central fiber.
Simplify something. In principle, you should have the difference of two curves at least.
Yeah, so there's a second subtlety, which is that we're replacing C with a curve. Okay, maybe I should set the prime now. Okay, so let's set a prime P that does not divide M. And then we'll replace C with a curve that represents the same congruence class mod P of M. Okay, or in particular represents a co-multiple. Yeah. So okay, so we get to replace our curve C with one transverse to the central fiber. So let me draw a picture. Need a big picture. I changed the colors. I'm sorry. The indexing of the colors changed. Okay, so this was our toy picture of the central fiber. In the case of our theta matroid. Okay, and now we have C naught contained in this central fiber, which is our replacement intersected with the central fiber.
C is not a complete intersection or anything.
So yeah, what we actually do is we take the closure and then we like resolve the ideal sheaf of that, and then we take a vector bundle, we projectivize that and take a relative hyperplane section. So in the end, it's kind of like a complete intersection with hyperplanes in a relative projective bundle. So it's not, yeah. So no, it's not a complete intersection though, in the sense, yeah, it's not a complete intersection in X of R. But we get some curve. Some wiggly curve. Okay, so I'm mixing my real and complex dimensions here. Sorry. That's our curve. And okay, so the key point is that, well, the curve is nodal. Its irreducible components correspond bijectively with irreducible components of x naught of r. Okay? And then like there's some kind of, yeah. So this is kind of what our curve looks like. Actually, sorry, let me keep this. Let me extract now. Extract some combinatorial information out of this picture. So first of all, we get a graph, which is the dual graph of this nodal curve. And now here are kind of the key facts. Okay, so the first fact is that if I take the weight graded 0 part of the Hodge structure on H1 of the curve, so I'm working in homology just because sort of more natural geometrically. So the Hodge structure on the first homology has weights -2, -1, and 0. Okay, so when we have a degeneration of curves to a nodal curve like this, the weight graded 0 part is the first homology of the graph. Okay, the second thing is that the weight graded 0 part of the first homology on the family of Abelian varieties. So that's actually this space M that we introduced before. This is the Z to the G dual. So this is the dual of the space where we realize our matroid. That follows from the matroidal construction. Okay. Okay. 3, well, we have a push forward map on homology from H1 of the curve to H1 of the Abelian varieties. That's just because we have push forward on homology. But in fact, we have a map that goes the other way from H upper one, sorry, H lower one of the Abelian variety to H lower one CT. So why do we have this map that goes the other way? Well, the Jacobian of X is a principally polarized abelian variety, and the Jacobian of C is also a principally polarized abelian variety. So using the principal polarization, we can dualize homology to cohomology and then pull back and then dualize. Okay, so we get a map both this way and the other way back. And now the condition that the curve represents M times the minimal class becomes the condition that this composition is multiplication by M. And then the final thing, which is maybe the most important piece of data, combinatorial data, is that we extract a coloring feed from the edges of the graph to the elements of the matroid R. So why is this? Well, we just see it from the picture. The elements of our matroid, our starting matroid, were exactly these 3 elements. The elements are blue, red, and yellow, right? And well, there's a coloring of the nodes of this curve, right? Which is that these are the blue nodes because they're the nodes that come from the blue nodal loci of the abelian variety. These are the yellow nodes, and these are the red nodes. Okay, so that's how we extract the coloring. And now this data allows us to deduce the following corollary. So corollary, if P does not divide M is a prime number, then what? Well, we actually get a splitting of H1G. Now, instead of taking coefficients in Z, I'll take coefficients in the field FP. The point being the multiplication by M is invertible over FP. And so now this is a splitting, right? Okay, so this is going to be H1GFP splits into M, but then tensored with FP. Direct sum, the kernel of iota lower star, also base changed to FP. So we extract this splitting, let me call it plus, and it satisfies the following two axioms. So if let's let Qi be the following quadratic form. So it's the sum over all edges of a fixed color. So in other words, under the coloring, I take all the edges that map to a fixed element of R, which is to say all of the nodes of this graph of a fixed color. And then I take the quadratic form EJ dual squared. Okay, so this is a linear function, EJ dual on H1. The square is a quadratic form. Okay, so this is a quadratic form on H1G FP. Okay, so that's so the point is that this quadratic form will exactly encode the monodromy of our curves over each of the coordinate hyperplanes. The Qi will be the monodromy about the I of the coordinate hyperplane, and these quadratic forms satisfy the following two key conditions. One is that essentially, if I take the monodromy of the curves and then I restrict to the homology of the abelian variety, well, I get the monodromy. Okay, I should have called it xi transpose, sorry. That's the first condition, and the second condition is that the direct sum decomposition is simultaneously Qi orthogonal. For all I equals 1 to k, the elements of the matroid R. Okay, and the proof that you have these is monodromy. The point is that the monodromy of the degenerating family of curves is compatible with the monodromy of the degenerating family of abelian varieties, and out of the compatibility of monodromy, you extract these things. Okay, 3 minutes left. I'm losing my voice. Sorry. Okay, so it doesn't really matter. The point is that there's some horrible linear algebra statement that we extracted. Ultimately, we just extracted some linear algebra statement out of the algebraicity of M times the minimal class. And this was the linear algebraic thing we extracted. It was there, a graph came in because that was the dual graph of the degenerate curve. And then we analyzed the monodromy of the curve and abelian variety, and we got this thing. So it seems like sort of hopelessly complicated to kind of work this out, perhaps, but maybe the final step is a sort of combinatorial deduces. Which says the following thing. There exists actually a universal R-colored graph, which we call the mod P Albanese graph, such that if G satisfies plus and the conditions, then, okay, so does L E of R. So in other words, there's some sort of universal graph that kind of satisfies these linear algebraic properties with respect to the matroid R and the prime P. And now the final thing is to do a computer computation. To say alpha2 of MK5 has no such solutions. And therefore, say the prime P equals 2, the initial hypothesis, which I erased, was that P does not divide M. So that's the thing that ultimately gets contradicted. And then just to define the invariant, because I didn't define it, it's the product over all primes P of the such that alb P of R has no solution to the linear algebraic problem. So sort of by virtue of its definition, it necessarily divides any algebraic multiple of the minimal Kerr class. Okay, so I guess I'm out of time. Thank you.
Great. Are there any questions?
Do you know? Our argument also proves that there is no curve C whose class mod 2 is this theta to the power 3 minus 1 divided by.
Whose class mod 2?
That's assuming it is a multiple.
Yeah. I mean, you can show that. I think I have to think. I'm not 100% sure whether, yeah. The problem is that, okay, you're on a very general fiber still? Okay. Yeah, I think it should be okay. Yeah, I think it should be okay because I think that so long as you can kind of make sure, I think you can replace that curve with another curve which represents the same class mod 2. It's the same trick, but then is nodal on the central fiber. And then ultimately, when you pass to the field F2, you extract the same linear algebraic statement because it reduces in the end to the right class. So yeah, I think it should be okay.
I think it's not a little clear, like, so what is the non-very general condition?
Yeah, well, it's definitely a condition. Like, for instance, I mean, what's the I mean, it's away from a countable union of subvarieties, and you really need that. Like, for instance, for cubic threefolds, for instance, like there's a countable union of subvarieties of codimension 3 for which the intermediate Jacobian does satisfy the integral Hodge conjecture. So you have this countable union of 7-dimensional subvarieties. And so that, like, somehow, like, you can't do something on the level of like points. In some sense, you need to work over like a field of transcendence dimension 10 to see you need to kind of see the full 10-dimensional monodromy cone. Like, in fact, you can show that if you take any one parameter degeneration of PPAVs, there exists a topologically trivial deformation of that one parameter degeneration that does satisfy the integral Hodge conjecture. So that sort of proves that you can't prove it only looking at one parameter degenerations. And with this example for the cubic threefolds, this is kind of cool. Like, you start over a 10-dimensional polydisk. If you slice it by a 9-dimensional polydisk, the invariant still is 2. But once you slice by an 8-dimensional polydisk, it goes down to 1. So then you lose the invariant over an 8-dimensional. So you need it's fundamentally uses the fact that the base has high dimension, kind of.
Does that include the Jacobian locus? For example, that family is like the locus where the fibers are Jacobians.
Right. Yeah. So the Torelli locus, like, I mean, the way to think about it in terms of monodromy cones is that, I mean, the Torelli locus is exactly kind of tropicalizing to these co-graphic monodromy cones. So the quadratic, there's like monodromy cones, which are in the space of positive semi-definite G by G matrices. And there you're taking the span of xi squared where it's co-graphic. So then these other regular matroids have already been studied actually in the context of toroidal compactifications of AG. They're called the matroidal locus. So they have lots of interesting properties. Yeah.
Other questions?
It's the main thing I know. For a while, there were various people who thought they could find a counterexample to the Hodge conjecture, but it's a tropical counterexample. I wondered if maybe this thing was a completely tropical formulation.
Yeah, so there is a totally tropical formulation in terms of like the tropical Hodge conjecture. And I think these should give counterexamples to the tropical Hodge conjecture, but it's a little tricky just because they think about things in terms of the point is that you have to take your tropical abelian variety so that its tropical generic point is the whole 10-dimensional cone. In other words, I shouldn't take like a rational vector in this 10-dimensional monodromy cone. I should take like pi times the first generator plus e times the second generator plus, you know, some, in other words, 10 like rationally independent. I should take a vector such that the smallest rational space containing it is 10-dimensional and sort of sees the whole cone. So then I think if you take the tropical abelian variety associated to such a vector, then that should in theory give a counterexample, you know. Okay, I'm just referring to the 10-dimensional example just for in the examples, but yeah, in general, yeah, you should take a very general point of the monodromy cone. Yeah.
Okay, let's then do it again.